Good morning, friends. I'm Tapan Trivedi, and today's session is on basics of electrical and electronics engineering for Marwadi University. Um, I'm going to discuss the last unit number 9, that is operational amplifiers. Okay. Um, let us see some objectives of this session. The session means the entire unit. So at the end of the unit, you are supposed to understand, or you will be able to now the outcome. This is called the objective or the outcome. The objective are divided into two. One is the principle and operation, and the other is the application of the operational amplifier. First we will understand the basics of operational amplifier, and then we will understand the application of operational amplifier. In the basics, the very first objective is that the student should be able to describe the basic operational amplifier and its characteristics. Second, the students will be able to explain what is negative feedback in the operational amplifier. Third, uh, you should be able to determine the application of operational amplifier. That means uh, where and when you can apply the operational amplifier. Uh, then we have certain applications, like you should be able to analyze the operation of several types of comparator circuits. Okay, we will see what is comparator and few other circuits also. So you should be able to analyze the operation of a comparator circuit, summing amplifiers, integrators and differentiators. Okay, these are some basic circuits based on the operational amplifier, and you should be able to understand and analyze those circuits, right? Okay, let us see how it all started. So in 1964, uh, there is a manufacturing company called Fairchild Semiconductor who developed this 741 IC. This is called 741. It's a integrated circuit. So the first integrated circuit designated 702, and it was developed by the Fairchild Semiconductor, and then it was followed by 709, and eventually we got 741. 741 is considered as a benchmark for the operational amplifier, and it has become the standard for industry also, right? um, so basically, what is operational amplifier we need to understand. So before this, we have gone through the bipolar junction transistors, right? So we know that bipolar junction transistors can be used for amplification, right? But when uh, the bipolar junction transistor has to be applied for proper amplification, then the circuit is not based on a single bipolar junction transistor, but we need to have several transistors, and those transistors together will give you satisfactory operation. So this was the overall schematic, right? Now this schematic was eventually converted into a single circuit. So the entire schematic was inside a single casing, and we call it an integrated circuit, right? This is called integrated circuit because you can't see this actually, but it is inside a single package like this. This is the physical 741. It looks like it has 8 terminals, right? And uh, inside this package, we have the entire circuit. So we call it integrated circuit. Now the integrated circuit, we have a single uh, we represent the entire structure or the entire circuit diagram with a single symbol, and we call it an operational amplifier, right? So all this we have, let us say we have one number, we have two number, three number, right? Five number is here, then six number, seven number, four number, and eight number is for no, it's not connection, no connection. Okay, so so this way uh, the developers came up with a single integrated circuit. You can see that it is written here 741, right? Now, what is this operational amplifier? So before I go with the symbols and other things, let me tell you something. We know that there is something called amplifier, right? Now, amplifier deals with the signal, right? It normally, we know that amplifier will amplify the signal. That means it will increase the amplitude of the signal from a weak signal of let us say 1 millivolt or 2 millivolt to uh, a signal of let us say 1 volt or 2 volt, right? That depends on how you want the output. um, so operational amplifier means you can operate the signal. You can add to signals, you can subtract to signals, you can differentiate signals, you can integrate signals. So that means you can perform the basic operations of which are mathematical. So you can perform basic mathematical operations on this operational amplifier, right? Using this operational amplifier. So that's why we call it operational amplifier, or in short we call it op amp, right? So it's written like this, op amp, op amp. The symbol is like this. Now the operational amplifier symbol is represented by this. This is a triangular. There are two inputs and one output, right? So a standard op amp has two input terminals. This is called inverting input, and this is called non-inverting input, right? Uh, why we call it non-inverting? Because when you give signal to this plus terminal, then the op amp will treat it as it is. Whereas if you give signal to inverting terminal, then the op amp will invert the signal. That means the positive one will become negative one, right? Additionally, we have supply also. We know that amplifiers cannot run without supply, right? And because we are dealing with uh, most of the signals are bipolar in nature, so there are two DC supplies, plus and minus. For example, plus V can be plus 12 volt and minus V can be minus 12 volt. And of course we have a ground also, which is not shown in the figure here because this is a symbol, right? So most op amps operate with two DC supply voltages. One is positive and the other is negative, right? Okay. Now, when we study any device, particularly electronic device, right? Then we want to see some ideal characteristics or desirable characteristics uh, of the device, right? So 741 or the operation amplifier in overall, um, it has some ideal characteristics like this. And one is infinite voltage gain. The first of all, let us understand what is voltage gain. The voltage gain is the output to input ratio, because we are using the amplifier to amplify the signal, right? As I said, 1 millivolt signal is converted into, let us say, 100 millivolt signal. So 1 millivolt is the output here, and 100 millivolt is 1 millivolt is the input here, and 100 millivolt is the output here. So then output to input ratio, let us say, is 100 millivolt divided by 1 millivolt. So that ratio is 100, right? That means we are able to amplify the signal 100 times that of the input. This is called voltage gain. Okay, how much you gain, that's why it is called voltage gain. So it is basically output to input voltage ratio. Now we want that this circuit should provide infinite voltage gain. That means the voltage gain is very high, right? Of course, because we are talking about the ideal characteristics, so we expect that the voltage gain is infinite. In practice, it cannot be. Okay. Then we have infinite bandwidth. The bandwidth is something, it's a range of frequency over which it can operate satisfactorily. Okay. For example, let us consider one signal, right? Now, a signal can have a frequency of 10 hertz. The frequency can be 100 hertz, it can be 1000 hertz, and it can even be 20 kilohertz or 1 megahertz in case of communication circuits, right? It can be even higher. So the range of frequency, we deal with different types of frequencies, right? And we want to ensure that over the range of frequency, the the op-amp is operating satisfactorily, because and it gives the same kind of response. Let us say the signal is 2000 hertz, and instead of 2000 hertz, now the signal is revised to 3000 hertz. Still, the operational amplifier circuit will give you the similar kind of output or similar kind of response without any kind of uh, performance compromise. So then the range of frequency over which this can operate satisfactorily is called the bandwidth. Okay. There is a question, what is inverting terminal? And so it will become very, very clear when I come back to this point, right? I know that you may be a little bit confused about what is inverting terminal and what is non-inverting terminal. We have a separate section on this, at what is non-inverting terminal and what is inverting terminal. So I will tell you what are these terminals, right? Don't worry. Okay. We have infinite input impedance. Okay, that means the input impedance is infinite. That means here it behaves as open circuit. And why do we need infinite input impedance? Because there will be an input signal here, right? Let us see. We have an input signal here, right? Now this input signal can be anything. It can be a signal coming from transducer. It can transducer means sensor, right? So this signal will normally come from the sensor at the input side. Now you know that the signal which is coming from the sensor, it may be very, very big, right? So let us take an example of brain wave or the heartbeat. So if you try to detect the heartbeat, then that signal is very weak, right? Now, if you want to operate this signal, then you must amplify it. Okay. Now, when when the signal is already weak, we want that the current which is flowing through this input path should be very, very small, right? So what we want is that this impedance, or you can say resistance, in a very simplistic manner, you can call this a resistance, let us say, right? So this resistance or impedance should be infinite. It should be very, very high, so that the amount of current which will flow and the input circuit is almost zero, right? On the other hand, what we want is that output impedance, which will be somewhere here, right? The output impedance should be zero, right? And why we want such a thing? Because there is an input signal, let us say 1 millivolt, and there is an output signal 100 millivolt. Now the output impedance is in series here. Okay, practically the output impedance is in series. So if, let us say, there is 100 millivolt, right, then if there is an impedance at the output, then there will be a drop also, and that drop will depend on how much resistance is connected on the output side, that is here, right? So it is expected that the output voltage remains the same irrespective of the uh, output current. So ideally this output impedance should be 0, right? Now a practical operational amplifier may approach these characteristics, but it may not fully achieve these characteristics. For example, the for example uh, the voltage gain, this voltage gain, it can be in thousands, but it cannot be infinite. Similarly, the input impedance, this impedance can be in mega ohm, but it cannot be infinite. It is in mega ohm, it may be in hundreds of kilo ohms, but it cannot be infinite. Similarly, the output impedance can be very, very small, like only few ohms, right? But again, it cannot be 0. So the practical operational amplifier may approach these characteristics, but it may not fully achieve these characteristics, right? Okay, now we have a poll or a quiz, we can say, right? I'm going to give you this link, right? You will get this link in the chat section. There is a link in the chat section. If you open this link, you will see that there is a question like this. If you have any query related to this link, you can simply post your query in the chat section. Okay, so there is a quiz for every student. The answer may be different. Okay, for few students it may be A, it may be C, because the answer order is shuffled. So the actual one will be, may look different than this. What I expect is that you should answer this quiz, and if anybody has any query, please let me know in the chat section. Okay, your answer will be automatically recorded when you submit the answer. Only thing is that you should write your enrollment number and the answer that you think is the correct one. Okay, you simply answer this, you submit it, your answer will be recorded. Okay, I will get answer from all the students. Again, based on your answer, your enrollment number and your answer, you will get the attendance. So please do not write your, again I'm telling you, most of the students have written their enrollment number and name in the chat section. But as I said, based on your enrollment number, your attendance will be counted. Okay. Now I think we already had enough time. Okay. So let us go forward. I hope everybody is fine. Okay. Somebody wants me to send the link again. Okay. Let us go ahead. Now, the practical operational amplifier. So, as I said, a practical operational amplifier will look like this, because a practical operational amplifier has uh, both the voltage and current limitations, right? Uh, for example, you cannot get a voltage uh, above certain value, and similarly, the current will also be of certain amount which you cannot exceed, right? So an operational amplifier, any device will have both the voltage and current limitations, right? For example, in operational amplifier, the maximum output voltage is plus or minus Vd. That means the output voltage maximum can be plus Vd and minimum it can be minus Vd, where Vd is the supply voltage, right? So the output, maximum output that we can get from the operational amplifier is limited by the supply voltage. Okay. Similarly, the output current is limited by power dissipation. For example, a 741 IC, which we have seen earlier, it has a output short circuit current of 25 milliampere. That means if I short this terminal, the meaning of short is that if I short this terminal with the ground, then the maximum current that should be allowed at the output is 25 milliampere, and the total power dissipation of this IC cannot exceed 500 milliwatt. 500 milliwatt, that is 0.5 watt. So if the power consumption in this IC exceeds 5.5 watt, then it will be damaged. So it is, you can understand, it is very delicate device, right? Another thing is that there is a noise. Of course, it is not part of this. You can see that we have a input impedance here, and then we have output impedance here, right? So input impedance should be near to infinite or as high as possible, and the output impedance should be near to zero, right? Fine. Now noise. So because we are trying to amplify the signal, at the same time we are also amplifying the noise, right? And noise is an undesirable signal that affects the quality of a desired signal. Okay, for example, uh, when I'm speaking, if there is any background noise, or there is any uh, noise in my background, then it will also be amplified, and that will reach to you, and then uh, the voice that you hear, it will be unpleasant if the background noise is unpleasant, right? So that's why the noise is considered as an undesirable signal. Okay, for example, you should only listen to what I'm speaking right now and not what is happening in the background, because what is happening in the background is the undesirable signal for you, right? Fine. Now the block diagram of operational amplifier. Okay, so it is, again, it is a device like this, and what is inside this device or integrated circuit. So we have three stages. Okay, one is called, the very first is called differential amplifier input stage. Second is the output of this is given to voltage amplifier, so voltage amplifier gain stage. And then we have a push pull amplifier output stage. What are the roles of these amplifiers? So the differential amplifier is the input stage for the op amp. It provides the amplification of the difference voltage between two inputs. So whatever is the difference between these two, V in is equal to the plus signal minus this signal. Whatever is the input bit, whatever is the difference between these two, that one is the that one is amplified in the differential amplifier, right? Then we have a voltage amplifier. The second stage is usually an amplifier that provides the additional gain, because first we had differential amplifier which is amplifying the signal, of course, but this amplification may not be sufficient enough. For example, you have studied in common emitter configuration in bipolar junction transistor that the beta is can have a maximum value of 500, right? Practically it can have a maximum value of 500. Okay, and in the practical condition it may be nearly 100, right? But what we want is the infinite output gain. Okay, so if we want infinite output gain, then the signal which is amplified to 100 times, let us say, should again be amplified 100 times. Then we can get a very, very high gain. This is just for your understanding. Okay, so the second stage is usually an amplifier that provides the additional gain, and some operational amplifier may have more than this voltage amplifier gain stage. And the third one is the push pull amplifier. This is a different type of amplifier, and this it is basically used to increase the current strength. Okay, now we know that uh, there is a voltage strength and there is a current strength, right? So first two are mainly used for the voltage strength, and the last one is being used for the current strength. Okay, and this way we get the output. Okay. Okay, now the term differential comes from the amplifier's ability to amplify the difference of two signals, that is v difference is equal to v plus and v minus. Now only the difference in the two signal is amplified. So if there is no difference, then the output will be zero, right? Okay, now the differential amplifier exhibits two modes of operation. So we are going to see uh, two modes of operation based on this, right? Differential mode of operation and common mode operation, right? There are two modes of operation: differential mode of operation and common mode of operation, right? Now if you have any question or any query up to this point, please raise your question or query, right? And this is the appropriate time to answer it, please. Okay, So somebody is asking me, can I again explain the block diagram? See, what is inside 741 or operational amplifier is the circuit, but that circuit is effectively divided into three blocks, right? The first block is called differential amplifier input stage, okay, which takes the difference of the input signal of this plus terminal and the minus terminal, right? So we get this signal minus this signal, and then it is given to differential amplifier input stage, right? Why it is called differential amplifier? Because the difference of the input is amplified, right? Now the output of the differential amplifier input stage is given to the voltage amplifier gain stage. This is another amplifier which is used for amplification, right? But this amplifier, the second amplifier, is actually amplifying the signal which is coming out of this out of the differential amplifier, and then the output of the voltage amplifier is given to the push pull amplifier, right? uh, the role is that the differential amplifier is the input stage for the op-amp, and it provides the amplification of the difference voltage between the two inputs, whereas the second stage, okay, what is the voltage difference again? For example, we have a 3 volt, see, let us say we have 3 volt on the plus terminal and 2 volt on minus terminal, right? Then this amplifier will amplify 3 minus 2, that is 1. So effectively we are having 1 volt as the difference, and this 1 volt is considered the input signal, and then it is amplified. That is called differential amplifier, and it is called voltage difference, okay, right? Now the second stage is usually an amplifier that provides the additional gain, whereas the third stage is the push pull amplifier. And if you want to see, it is available right here. The blue one is the differential amplifier,